Welcome back. In recent videos, we've been developing a whole bunch of skills that will allow us to answer counting questions. The goal of this learning objective is to take all those skills and put it together so that you'll be able to answer any counting question. So we want to know, let's say you have a counting question, what's the best way to approach it? There'll be a couple of questions along the way that you'll want to ask that can give you some direction when you're trying to figure out what should I do next. First question. Does your question break down naturally into multiple cases? So if it does break down into multiple cases, you'll need to ask a second question, which is, are these cases disjoint? If you have multiple cases and they're all disjoint, use the additive principle to count each case separately and then add the answers together. Now sometimes those cases are not disjoint, in which case you'll need to use inclusion-exclusion. We've seen the two-set case, where the size of the union of two sets is equal to the size of the first set plus the size of the second set minus the size of the intersection. And in the next learning objective, we'll see how to do this when there are more sets. Let's look at a quick pair of examples that look almost the same, but require recognizing that in the first case, the sets are disjoint, whereas in the second case, the sets are not disjoint. This question asks, how many 8-digit passwords using the letters A through Z start with an A or a Z? Well, we're seeing the word or appear. That's often a good clue that says we want to break something down into cases. And we can see that the words look like A and 7 more letters, or Z and 7 more letters. A password can't have both an A in the first letter and a Z in the first letter. So those are two disjoint cases. We know that the first case has 26 to the 7 solutions, and the second case also has 26 to the 7 solutions because there are 7 choices to be made, each of which has 26 different options. And so the final answer would be the sum of those two answers. If instead the question is how many 8-digit passwords using A through Z start with A or end with Z, then we see that our objects look like A and then 7 digits, or 7 digits and then Z. Now, it is possible for a password to start with A and end with Z, and so these sets are not disjoint. We would see that the first set of objects has 26 to the 7 solutions, the second object has 26 to the 7 solutions, and the intersection would have 26 to the 6 solutions, and so the answer here would be 26 to the 7th plus 26 to the 7th minus 26 to the 6th, following the principle of inclusion and exclusion. Sometimes your question doesn't break down into cases. Then you could ask yourself, is it easier to count the objects that are not in your set? So for example, let's say you had a question that said, how many 8-digit passwords using A, B, C up to Z have a repeated letter? The thing we might notice is that the set of passwords that have a repeated letter are the same as the set of all words minus the set of words that do not have a repeated letter. And so the answer to the question would be the set of elements that are in the universe, but not one of these bad words that have no repeated letters. When you're faced with a situation like this, you count the elements in the universe, you count the bad elements, and you subtract out how many bad elements there are. So in this question, the size of the universe is the set of passwords with repetition, which is 26 to the 8th. The size of the set of bad words is the set of passwords without repetition, which is P of 26, 8. And so the number of words that we want is equal to 26 to the 8th minus P of 26, 8. It's also possible that the question that you're investigating can be seen as a larger question that's a sequence of smaller questions, where the number of options at each step does not depend on earlier choices. In that case, we apply the multiplicative principle. A keyword in this type of situation would be and. If you see something where you need one thing and another, that's a clue that you would need to use the multiplicative principle. And so let's take a look at an example. In how many ways can you roll a blue die and a red die and get an even blue number and an odd red number? One way to do this is to say that the set of even numbers on a die is 2, 4, and 6. The set of odd numbers on a die is 1, 3, and 5. And so the multiplicative principle says that the answer would be 3 times 3, or 9. Now we could also represent this as a tree diagram where there are 3 possibilities when you roll the blue die, a 2, 4, or 6, and then for each of those 3 possibilities, when you roll the red die, there are 3 choices. 1, 3, 5, 1, 3, 5, 1, 3, 5. The key thing that's happening is that the number of choices at this second step does not depend on what the first choice was. Whether we had a 2, a 4, or a 6, there were still the same number of options. And this brings up the most important part about using the multiplicative principle, which is you cannot apply them when later choices do depend on earlier choices. So if the question is instead, in how many ways can you roll a blue die and a red die, so you get an even blue number and a sum of at most 7 on your 2 dice, in that case, we can still roll a 2, a 4, or a 6 on the blue die, but the number of choices that are allowed on the red die depends on what the blue die was. If we roll a 2, to have a sum of at most 7, there are 5 options. You could have a 1, a 2, a 3, a 4, or a 5. But if you roll a 4 blue die, then there are only 3 options, a 1, a 2, or a 3. And if you roll a blue 6, there's only 1 option for the red die. And so we can actually count how many different possibilities there are using this tree diagram. There were 5 choices here, 3 choices here, and 1 choice here, for a total of 9 ways to do this. But we would not be able to use the multiplicative principle because the number of choices at later steps depends on what the earlier process gave. Let me add a couple more words of wisdom. Once you've gotten your question down to a simple counting question, it's very important to know exactly what you're counting. In this case, I highly recommend going and reading section 1.7. It has a list of useful questions to be asking yourself. It's very helpful. You should read it. You should read it multiple times. You should take notes about it. You should digest it, and you should internalize it. A couple of points I want to reinforce. To figure out exactly what you're counting, you should write down a careful list of the objects so that you can understand the structure of the list. You should be asking yourself, does order matter? Are you dealing with a list or a sequence? Are your objects labeled? Are you dealing with a set or a multi-set? Are your objects indistinguishable one from the other? And is repetition allowed in the set of objects? This is where we go back to the chart that we've been building all this time. If order matters and repetition is allowed, then you have a sequence of length k. And we know to count that, we use n to the k. If order matters but repetition is not allowed, those are our k permutations, and we know that there are p of nk of those. If, on the other hand, order doesn't matter and repetition is not allowed, those are when we had our k subsets or our k combinations, and we know that there are n choose k of those. And if we're in the case when order doesn't matter, but repetition is allowed, those are the k multisets, and those are counted by n multi-choose k. You now rely on the counting skills that we've developed so far, and practice, practice, practice. Keep looking at examples, keep making up new examples and sharing them with your classmates. Do what you need to get enough experience so that when you look at a question, you know how you want to approach it. All right, good luck. I'll see you next time.